Now I want to talk to you guys about regularization techniques, which are ways to fight overfitting. Overfitting, as you hopefully know by now, is when the model starts to do worse on the validation set, but better on the training set. In other words, it's when the model starts to memorize the training set instead of just generalizing on unseen data. This graph here represents the loss over time. So on the x-axis, you have the epochs, and on the y-axis, we have the loss of our validation set and also our training set. You can see that as the training process continues, the training set goes downwards, which we've learned to expect. But for the validation set, we see that the loss goes down, but then at a certain point, it turns and goes back up. And at that exact point, that's when overfitting starts to happen. Here's another way of looking at it. So instead of graphing the loss, we have the features and the actual output values that we're trying to predict. If we have a decent model, we could have a line like this, a simple best fit line that goes through our data. If your model overfits on the training data, it'll look something like this, where it tries to go through every point exactly to make sure that it does well in terms of the training loss. But then because of this, it can't generalize, right? If you look at these two graphs here, try and ask yourself which one would be good to generalize, meaning which one would do better on unseen data. If you have this best fit line here that goes generally through the middle of all the points, this one can generalize better because it can approximate the general idea of where these points would show up, but this one goes through every specific point. So if we put some new unseen points on here, it will be farther away. So with that said, hopefully you guys understand what overfitting is and why we don't want it, because we want a model that is able to generalize on unseen data. So with that said, regularization, it's hard to say that, regularization, it's a set of techniques that fights overfitting. So there's a bunch of different steps that we can do to help lessen the effect of overfitting and also delay it, okay? So one of these is early stopping, which we're already familiar with. This is something that we've been doing from the very beginning when we made our very first neural network. Whenever we plotted our validation and training loss over time, or epochs, we saw when the model started to overfit, that little point where it turns the other way for the validation set. And what you can do is stop the model training process early by figuring out what epoch it starts to overfit and retraining the model up to that point instead of retraining it all the way up to where you stopped before. So stopping the model training process at that epoch right before it starts to overfit will give you a better model than otherwise. Because of course we want the lowest loss, right? So that's just one technique that you can do. Another one is to decrease the complexity of your model. So I'll give you a demonstration of what I mean by that. First of all, this notebook is from Deep Learning with Python 2nd edition, just like a lot of my code. But let's go back down here now to improving generalization. And then the section says reducing the network size, which also means to reduce the complexity of the model. I showed you guys a little bit before that when you increase the complexity of your model, which means the number of layers and also the number of neurons in those layers, this has a tendency to make the model overfit more quickly. And if you just think about why that is, if you give your model a lot of resources in terms of its architecture, let's say it has more layers and also more neurons per layer, like, 256 instead of 16, the model will have more capability to memorize more data inside the training set. So during the training process, when the data passes through the model is going to use all of its resources to memorize as much as it can, because the whole goal of the learning process is to minimize the training loss. At least that's what the optimizer is trying to do, right? The other side of that is when you have a really simple model and it cannot really capture any patterns in the data, so it's going to underfit in that case. So you really just want to find the sweet spot between a model with too low complexity and a model with too much complexity. It's overly complex, because if it's overly complex, it will overfit. So one of the things that you can do to regularize your model to prevent it from overfitting is to reduce that complexity, okay? So just as an example here, we're making a model here that will do our binary classification with the IMDB dataset that we did before. So it's going to bring it in, pre-process it, and then build a simple model here. So it has 16 neurons in the first layer, 16 in the second layer, and then one output neuron, because we're doing binary classification. So we're going to train that one, and then down below that, we're going to make a second model that is less complex. So it has the same number of layers, but the first hidden layer and the second hidden layer has 4 neurons instead of 16. So it's a lot smaller than the previous one. And then we have a third model that is way more complex than both of them. So this one has 512 neurons in both the hidden layers and still one output neuron. So if we plot those neural networks after training them, this is what we get for the validation loss. You can clearly see that with the original model, the dotted line, it starts to overfit more quickly than the smaller model does, which lines up with what I said. A more complex model has a tendency to overfit more quickly. Same story with the other comparison. So if we plot the validation loss of the original model and the larger model, we can see that with the larger model, it starts to overfit way more quickly than the original model. So again, that lines up with what I said. I'll just repeat it again. The more complex your model is, the more it has a tendency to overfit. That is why one of our regularization techniques is to decrease the complexity of our model. Another technique for regularization is weight regularization. It's hard to say. This is when you essentially penalize larger weights to prevent overfitting. The way it does that is it adds on to the loss function calculation. You have L1 regularization and also L2. L1 works by taking the absolute value of the individual weights and adding them together, so summing them up, and then multiplying them times lambda, which is just how much you want to essentially regularize it. But doing this, of adding this calculation to the end of our loss function calculation, this will have the effect of making some of the weights in our layers equal 0. Therefore, it creates something called a sparse model because all of the weights are not filled in with actual values. A lot of them are going to be 0. But basically, this has the effect of also feature selection, which means that it's going to select the most important features for the model training. So this version of regularization using L1 is really good for when you have a lot of features that you're feeding into your network, and not all of them are super important for the training process, for actually getting a result that matches the training set. So for example, if you're feeding in like 1,000 features into your input layer and that goes through your network, not all of those 1,000 features are going to be very important. So adding this regularization to your layers of your network will zero out some of the weights and also make it so that it selects the most important features. So really the key behind L1 is it does zero out those weights, forcing the model to learn some of the general features of the dataset, the ones that are most important, and not focus on specific samples. Because again, overfitting happens when the model memorizes the training set and doesn't generalize very well. So actually killing or disabling those connections, the weights, will have that effect of preventing overfitting, which is cool. So when it comes to L2, this is very similar, except that it's doing a different calculation here. Instead of summing the absolute value of the weights, it's just going to sum the square of the weights. So square each of the weights, sum them up, and then multiply it times lambda. This will have the effect of moving all of the weights of the layer near to 0, but not 0. So it just influences the model to have smaller weights instead of larger weights. So this in a different way prevents overfitting because it reduces the impact of certain weights becoming too large. And it generally moves all the weights to a smaller range of numbers, which, as we learned before, neural networks prefer. L2 is more recommended for general purposes. So if you're creating a new model for the first time and you're not really sure which one you want to use, then I would say just go with L2 and just play around with it to see what results you can get. So that's what those do at a high level. Hopefully that makes sense. But the general idea is that it helps prevent overfitting. So it's another regularization technique. Let's jump into our code now to see how we can actually apply it. All right, so to demonstrate this to you, I'm going to be showing you guys how to add regularizers to the network that we already built for the binary classification problem that we did before. So here's the architecture of the network. So it's just a sequential model. It's got two dense layers in the middle, so 16 neurons and 16 neurons, and then an output layer with one neuron. Let's go ahead and run the model real quick just to see what we have right now. And then we can compare that to what we get when we add the regularizers. Regularizers? Whatever. Okie dokie, so it's finished training now, and this is our training and validation loss plot. So we can see that it only did 7 epochs. By the way, there is a callback, the early stopping callback. So if it detects that it starts to overfit, it has a patience of 3. So if it detects that, it will stop the process earlier. So yeah, it stopped it at 7 epochs because clearly it starts to overfit at epoch number 4 because it goes upward after that for the validation loss. So it starts off around zero point 0.4 and then goes down to just under 0.3 and then overfits. And then the training and validation accuracy, you can see that the training accuracy goes up to 95%, but then the validation accuracy sort of stays around just under basically 88% or just under 90%. So, and then if we look at the final results on the test set, we can see that we have a loss of 33.33 and then an accuracy of 87%. All right, so to add L1 and L2 regularizers to your network, you can add them to the layers that you already have. So for example, this first hidden layer that we have here, we can do comma, and then we just type kernel with an E, underscore regularizer right there. And then now you can specify which one. So we can do keras dot regularizers dot, and you have all these options here. So you have L1, you have L2, and you have L1 and L2 combined. L2 is recommended as like the default one that you use if you don't know which one to use, because it's generally great overall. And now inside of here, you need to only specify the regularization penalty. So the higher the number is, the more it's going to penalize it for higher weights. So the default for this will be 0.01. So we'll just do that. I know it's the default, but we'll just put it there so we know exactly what it is. And we're going to go ahead and copy this to the other hidden layer as well. There we go. So now we have added a regularizer, the L2 regularizer, to both hidden layers. So now I'm going to retrain the model and see how it affects the training process. So while it's training, you can see here that we start to overfit really quickly after only 4 epochs, which is really, really fast. Which is, not always a bad thing. This also means that the model is learning very fast because we get a very high accuracy pretty much from the get-go. but of course we want something higher than 90%. So the idea behind L1 and L2 is to prevent overfitting or delay it, and L2 specifically is really good at smoothing the curve in terms of the validation loss. So here's the results for this. You can see that kind of like I just explained, the validation loss, it does seem to be overfitting a little bit later, not quite as late as we would want it to, because it's still only 12 epochs where the model cuts off. But it does take longer to overfit, and also the loss does not get as low as before, because before we had under zero point 0.4 and it got down to just under zero point 0.3, but now we're starting at zero point 0.6 and we're stopping not even under zero point 0.4. So you could say that the L2 regularizer is working because it is delaying overfitting, but it still does overfit pretty quickly after only 10 or 12 epochs, and it does not get you that loss that you would want otherwise. So just like everything else, it's a trade-off. You want to find the correct regularizers just by playing with the different options that you have, but also play around with the penalty that you provided. So if we change it to something like a smaller number, like 0.002, for example, let's see how this affects the output. All right, here we go. You can clearly see that there's not much of a change. You can see that it cuts off pretty early still, but now that we've lowered the penalty, it is able to get under zero point 0.4, which is great. So now let's make it even higher. We'll do 0.2 and 0.2, and let's see what that gives us. So as you can see, it's extending all the way to epoch 27 so far, which kind of makes sense with what I've taught you so far. If the penalty of the L2 regularizer is higher, this means that it's going to try and delay the overfitting as much as possible, much more aggressively than otherwise, right? So that means it's going to take longer to learn, longer for the loss to go down, but potentially you should have a much more smoother loss curve. So let's take a look here. And here we go. We can see that it's much more stable than before. We can see that it does take much longer for it to start overfitting, which is great. That's how you know the L2 regularizer is working. Another thing that you'll notice is that it's more smooth. So you can see that there's not a lot of rigid, parts of the curve. And also the training loss and validation loss are staying hand in hand. They're staying pretty close together. So that's another great sign as well. But anyways, that's how you can add a L2 regularizer to your dense layers. It's really easy, but the tricky part is actually just finding that correct penalty. So you got to play around with that. But I think understanding what the trade-offs and how moving the penalty in one direction versus another affects the training process is really important. You can also use L1 if you want to. It's just simply changing it from L2 to L1. L1 again is good for feature selection. So if you have a lot of features in your, as input into your network, this will try and choose the most important ones, so to speak. Okay. You can also do a combination of L1 and L2. I believe it's just, yeah, it's that. So L1 underscore L2, and that will literally just combine it. And then you just need to provide two penalties now, for L1 and then L2, and then you can change them to whatever you think fits. So let's make both of these 0.2, and let's just see what we get. Oh, it looks like I perhaps typed the wrong one. There we go. It's just that. So L1, L2 with no underscore. All right, so clearly this is not the correct options for these L1 and L2 regularizers that we added, because look how bad this is. This is horrible. It does look a lot smoother, which is characteristic of the L2 regularizer. It smoothens the process, but you probably want to decrease that maybe, or just take off the L1 maybe. It really just is an art, more of a science, where you just gotta play around with it. But that is it. That's how you can add L1 and L2 regularizers to your dense layers. So the last technique that I want to teach you guys for this episode is dropout. Dropout is when we randomly turn off or disable a certain portion of the neurons in the network. So in TensorFlow, dropout is a layer, and you pass a hyperparameter to that, which is the dropout rate. So it's a hyperparameter p, and the dropout rate is essentially the fraction of neurons you want to drop from the layer. So for example, if you have a layer with 10 neurons in it, and your dropout rate is 0.5 or 50%, then 5 random neurons will be disabled. And you can basically hook up these dropout layers to different layers. You can have different levels of dropout. So at the beginning, if you want a higher rate of dropout, you could set it to 0.5. And then at the very end, if you want a lower rate of dropout, you could set it to like 0.3, for example. So the idea is that you want to find that sweet spot of the dropout rate. You want to not disable too many neurons in your layers, because then you would underfit. You would not be able to capture meaning. But if you can disable the right amount of neurons in your layers, then you can fight overfitting. This is because disabling neurons prevents the model from becoming too reliant on certain neurons. Very similar to what we did with L1. L1 basically disables certain weights of your model layers. Dropout disables entire neurons, so it prevents the model from relying on certain connections to different neurons. And since it basically breaks those connections, it encourages generalization. And I think intuitively that kind of makes sense, because I told you guys before that the more complex your model is, the more it's tending to overfit. And therefore, if we disable a certain amount of neurons in our model layers, we're decreasing the complexity of our model. We're forcing it to have to generalize instead of memorize different training samples. Okay, so I've reset the model here to show you how to add dropout to your model. So it's just our standard classifier with two hidden layers and then our output layer. So to add dropout to a network like this, all you gotta do is choose a layer that you would want to add it to, and then after it, you can do curious.layers.dropout. And now you just want to provide the rate or the fraction of the input units to drop as it says here. In other words, you're going to be dropping out a certain percentage of the outputs from the previous layer, okay? So if you were to do 0.5 right here, this would effectively disable 50% of the neuron outputs from the previous layer. And again, dropout is a way of making it so that your network does not rely on certain neurons, and that has the effect of making it generalize a little bit better. So this is the current output of our model. This is what it looks like now in terms of the training and validation loss at least. Let's just see how adding that 0.5 or 50% dropout to our two hidden layers affects that. Alright, so it's done training here. It's very hard to notice what the dropout layers did to affect this, but if you look very closely, we can see that it starts overfitting in the first model without any dropout very quickly. I would say epoch, I don't know, 3, 4. And then for the new one with the dropout of 0.5 added to both hidden layers, we can see that it starts overfitting a little bit later, but it's not really noticeable at all. So what I'm going to do is up the amount of dropout to a much more higher value of 0.8 for both layers. And let's see if this has any effect on the overfitting. Alright, so with that increased dropout, you can see a much different story here. You can see that it starts to overfit not until, I don't know, maybe epoch 16, 17, and even then, it still seems to be trending downwards for the most part, but it may start to overfit around this point, right? So as you can see, dropout is another effective way to make sure that your models don't overfit as quickly, and it also can stabilize the training process for the validation loss. Okay, guys, that's it for this episode. Hopefully, you guys learned a lot. I taught you guys some of the regularization techniques that you can do with your neural networks to prevent your models from overfitting as quickly. I taught you guys about early stopping, reducing complexity, L1 and L2, and also dropout. There are other techniques out there like data augmentation, but I just wanted to teach you guys some of the most relevant and useful ones for this episode. So I hope you guys learned a lot, and thanks for watching, everybody. Peace. So that's it for this video, everybody. I really hope you learned something new. If you liked the video, please hit the like button, and if you want to see more, hit that subscribe button. Make sure to also check the description below for important links to code and other resources, but also really important, join our Discord. We have a big community of over 5,000 programmers, and it's a place where you can find new friends or get help on any code that you're stuck on. If you want to support what I do on this channel, please consider hitting the join button below, and this will allow you to support my channel for as low as $1 a month, but there are different tiers to choose from if you want to. For anyone that becomes a member on my channel, you get a special rank on my Discord server, early access to new videos, and you can just see yourself on the screen right now. So if that sounds cool to you, feel free to join. If you don't want to, that's fine. If you can't, that's okay too. I really just appreciate you watching the video anyway. Thank you so much. And that's it. Peace.